Hello everyone, welcome to the counter equation introduction. We have a lot to go through in this video, so I'm going to have to kind of go through things quickly. This is the idea, of course, behind the counter equation is to come up with a formula that with reasonable givens can calculate the area of any polygon, no matter how crazy looking the polygon is. It could be obviously convex, like most normal polygons, or it would be concave, right? It could have as many concave angles as you can fit in it, all right? It can have whatever side lengths, however many sides. You know, obviously the more the sides, the more you're gonna have to calculate, at least the way I designed it. Here are givens. These are what I thought were reasonable givens. I didn't know quite what I wanted the givens to be when I first designed the counter equation, but I knew that they had to be reasonable. They couldn't be something crazy. They couldn't be like some weird line bisecting it. Maybe if it like made sense, or maybe if it made the equation much simpler, right? There's a give and take. I think these givens are reasonable. I think they produce a pretty, overall, when you consider what the equation does, a pretty simple equation, right? So these are givens, right? You need all the angle measures or magnitudes, right? And you need them in order, okay? You need all the side lengths, and you need them in order, okay? Now, the order, you just have to know what the order is, okay? Whatever order, like maybe you get them in, you need to order them going clockwise around the polygon, okay? That is all. As long as you're given the order going counterclockwise, as long as you know that and you can order it, list it where it's going clockwise around the polygon, then you're good to go, okay? So that's what this third given is. You basically need to know not just any order, you need to know what kind of order is so you can convert it, if it's not already converted, into a clockwise order, okay? That is extremely important, okay? Basically, we have at each corner, we establish our line, this right here, our line parallel to height equals 0, h equals 0, okay? So we're basically kind of doing that. If you guys can just give me a little bit of time here. We're doing that at every, pardon my drawing, at all the corners. We're establishing these lines that are parallel to the x-axis, or what we have established to be the x-axis, okay? The idea is we take our crazy polygon and very simply split it up into trapezoids or either triangles. The area for trapezoid also works for triangles, okay? It absolutely does, all right? The idea is that, you know, for area of a trapezoid, you got base 1 plus base 2 in parentheses times the height divided by 2, all right? Base 1 has a value that is like the height of this right here. Basically, these are sideways trapezoids, right? Okay. And then, but base 2 is 0, right? As you can see here, there's nothing there, okay? And so it's going to be 0 plus whatever this is, okay, times the height divided by 2. That's the area of a triangle. Base times height divided by 2. Okay, everyone knows that. So it actually works well when dealing with triangles too, okay? So you're either going to split this into triangles or trapezoids based on if there's anything there, right? So we got this right here. That's our first one, okay? By the way, probably should have mentioned this before. We starting with an angle, okay? So you, in your list going clockwise around the polygon, you will alternate between, starting with angles, you'll alternate angle, side, angle, side, angle, side, okay? So we label our first angle. You choose one of the angles, doesn't matter, okay? I'm going to say that is theta 1. And then the side going clockwise to that angle is going to be SL1, okay? And then the next angle, which would be this angle right here, that's going to be theta 2. Okay? And this will be SL2, theta 3, SL3, etc. And that's what you imagine the layout to be. Okay? Obviously, when you're using the counter equation, you're probably just going to plug and chug, right? You don't need to imagine all of this to actually use the equation. This is just to help you understand the equation, okay? This is the idea behind the counter equation, all right? So with our theta 1 here, we can imagine, yeah, this is an angle. It's definitely below 90 degrees, okay? We're going to say the sine here is positive and the cosine is also positive, okay? Now, starting from h equals 0, all right, we're going to add whatever the sine is here to 0. And we're going to multiply that. Obviously, that's the sine times SL1. You're going to do, like for here, it'd be, you know, the sine SL1 times the sine of theta 1. It's going to be a positive value. It's going to exactly be this height, in fact, all right? You know, plus 0, which is still this height. And then we're going to multiply that by the cosine of theta 1, which is going to get us this length right here, okay? That is parallel. This height is perpendicular to our established x-axis, of course. That's how trigonometry works, okay? Whenever you take the sine of an angle, it's going to be perpendicular to the x-axis on the unit circle, okay? And the cosine is going to be either on the x-axis or the unit circle, or you can imagine it like parallel, right? You know what I mean? You can imagine it wherever, but it's going to at least be parallel, okay? This area is going to be a positive area in this case, okay? And then we move on. I have to move quickly, so bear with me. We move on to theta 2, this angle right here. It's a big angle, okay? Now we can see in this, okay? We can see it's headed in this direction. The cosine is going to be a negative value, but what we're going to do for the height is going to be the sine, the side length, times the sine of our angle. Now it's going to be the angle relative to the positive x-axis. This is the angle. Remember, the starting point for every angle relative to the positive x-axis is always at when theta equals 0, essentially, when it's going in the direction of the positive direction, okay? You always start there, and then you go until the side, all right? That all gets explained in later videos, okay? So we can see here, obviously, this huge angle, kind of like you can see here, it's going to be, the cosine is going to be negative, and we have a positive height value. That's going to get us a negative area. From all the way over here to the beginning to here, I'm going to fill up this whole trapezoid with this blue marker. As you can see, it's also interacting with our previous trapezoid. There's overlap, right? In fact, it's overlapping with our first trapezoid in a sense that all this area is now 0. The area here has been erased, and now our total area is actually negative area. It's the blue marker, okay? This is all by design, okay? Because it all evens out and works beautifully in the end, okay? I'm going to have to go quickly here. I think you guys get the gist of it. Our next trapezoid is going to be with side length 3, okay? We got here, okay? Now, this, as we can see, the cosine is going to be a positive value this time. And even though the height decreases, it's still above height equals 0. So it's also going to be a positive value. So this whole thing from here, from that corner to this corner, going all the way down, is going to be positive area. Positive area. I got to be careful because I'm infecting the marker. Oh dear. Be careful with markers, people. So as you can see, we have positive area here, and now look what's happened. It encompasses both our previous trapezoids / triangles. Incredible. In fact, it now has canceled out with this blue area to make this 0, right? And it's added back to our 0 area here to give it back its positive value. So basically, we've essentially cut out our perfect slice. This the exact thing. We include the stuff we want, and we cancel out, we zero out the stuff we don't want. That is the idea behind the counter equation. We do this going all the way around the polygon. Can I get away with one more example? I'll do it for you. Okay, one more example. In fact, you're probably wondering, look at this. Oh my God, it bisects the line. Not an issue whatsoever. There is absolutely no issue with bisecting the line. It works out perfectly. I don't have time to do a detailed proof in here, but remember this. Essentially, in this area, we have positive value, and in here, we have negative value. That is the result of what is happening, okay? That is because our height here, right, it's positive. Our height here is negative. When we add those two together, they're going to cancel out. One will win out. So in the end, the overall height, so to speak, will be positive or negative. You're going to multiply it by the base. What that is going to do is you're going to have a net a little bit of positive area or a net little bit of negative area, okay? So the area this side generates is actually less area than this because there's some negative area here, okay? And that is intended because the very next side here is going to add a ton of positive area, okay? Let me show that right now. We can see that this side, everything is going on with this side length is very negative, okay? I mean, look at it. It's got this negative cosine value, obviously, and the height value, everything's below 0. The starting point and the ending point is going to be a negative value. But a negative times a negative is going to equal a positive, in fact. Hey, Simba. And so this area over here will be a positive area. In fact, it will, I don't want to draw over it, I don't want to taint the marker, it will conflict with our negative area over here. It will overlap that so that this is 0. It's going to zero out with the area here, and that is nice because we did not want to include that area. I don't really have time to keep going around the polygon forever and ever, okay? Now that you guys have seen this, I want you to look at the counter equation. It's going to be on screen right now, okay? You see some of the stuff I was talking about. Remember, I go into extreme detail on all of this in parts 1, 2, 3, etc. Okay, so the details get ironed out, but this is what we're modeling when we are using the counter equation. Okay, this is basically, you can imagine what's going on in the background. Okay, what was intended when I made the counter equation. What is happening? Okay. As you do the math, as you plug and chug. So I'm going to quickly go into misconceptions that are common with, or mistakes that are common when you're trying to model the counter equation, okay? Now, our starting, I don't know if you can, I've done so much wrong, I don't know if you can still see this. Our starting angle here is, in fact, an acute angle. It's an angle that is below 180 degrees. It is a convex. We'd call this a convex angle, okay? All right, and this angle right here, it's above, the interior is above 180. We'd call that concave, all right? This would make this, having one concave angle would make this a concave polygon. So our first misconception is when you're trying to model a concave polygon, I've gotten confused with this, okay? So our first misconception, or when our first angle is a concave angle, okay? It'd be like this, I don't even care at this point. Simba, wait. You wait a second. There we go. We have our nice concave polygon. Our theta 1, this huge angle, huge interior angle is our theta 1. But if you're trying to imagine it and you draw this, you've done something wrong, okay? In this, you can see, it feels like, oh, the angle, it's starting at the x-axis. It should be fine. It's going from the x-axis and it's going there. No, okay? This is the 180 degree mark. You have to start it at the 0 degree mark. So in the positive direction, not the negative direction, okay? The correct way to model such a polygon, as you can see, they're not perfectly the same. I tried my best to draw it the way it's supposed to. I think I did pretty good, right? You're supposed to rotate this almost to the point where it's upside down to get it where you can align it properly, okay? And I think I did a pretty good job. The size, obviously, I didn't mimic the size so well, but the shape, that's pretty good, right? That's pretty good. So we start from the positive x direction, not the negative x direction. Oh my God, monstrosity. We start with the positive x direction from theta equals 0, to this huge theta here. And this is our first, this is SL1, our first side length, okay? And then we're going clockwise around the polygon, okay? So this gets a check mark, okay? This is how you're supposed to model a polygon where your starting angle is a concave angle, all right? Concave, it makes the polygon concave. That's the point where it's concave, right? Concave angle, right? Okay, next point of confusion, and this is the last thing, I swear. Okay, our next misconception is when modeling, right? We have like a pentagon here, and you start at the wrong, you think that this right here, basically the next misconception, remember, we're going clockwise around the polygon, okay? We are not going counterclockwise, okay? Remember, on the unit circle, look at the unit circle, okay? You see how in like all the angle measurements, they all, this is like 30 degree angle, this is like a 60 degree angle. Why? Where are we saying this from? Because we're saying this is 0 degrees, okay? So it's all starting from 0 and then going counterclockwise around the circle to whatever angle measure you want to go to, 230, 260, all right? It's from the context of starting at 0, which is this positive x direction, okay? Remember, whatever angle measure your theta 1 is, if you're modeling it, it definitely can't be going clockwise around the unit circle. Remember, we're going clockwise around the polygon, but when modeling the angle, we're going counterclockwise as if we were using a unit circle. It is as if we are putting a unit circle on each and every corner of the polygon here. Each corner gets a little unit circle you put on there, and you imagine that, and you imagine that the x-axis on the unit circle is like a line parallel to our nice green line here. I drew these green lines here, right, on most of the corners on this example polygon, okay? So you're going to imagine you're transcribing that, all right? You're just putting it right on there, and then you get the angle relative to our positive x-axis, 0 degrees. You see? This craziness is the idea behind the counter equation. When you watch the rest of the videos, just keep this in mind. In fact, when you watch all the rest of the videos, I encourage you to come back to this video, the introduction video, and then it should all come together, okay? You'll see all of this get backed up perfectly, in my mind, perfectly by math, okay? And you will understand what were the whole components of the counter equation, okay? Hopefully you guys have enjoyed this video, and I hope you guys enjoy the counter equation series. I put a lot of work into it. I can't believe I was able to actually make a formula that can solve the area of any polygon. That was just so glad I was able to do that. It was incredible. Okay, bye guys.